data fitting problem, right? So what we had done, I think I'm just trying to make sure that the notation is correct. So we had this data x1 up to xn. So this data, these were like independent variables stored, the features if you want to call them. And you have the corresponding observations y1 up to yn. And we had said that there exists a model f from Rn to R, correct? And what does this model do? It actually is sending. So f of x is actually equal to y for every x in Rn, right? And what we have to do, you have to find out this particular function f. You have to find this particular function f from the data that you have observed, right? So these x1, x2, xn. So all these points actually belong to Rn, n-dimensional vectors, and all these are actually the corresponding observations there in R. So that is the function going from Rn to R. And then we said we will have a function. So this f hat, this was a model. We said we will build this model from Rn to R. And how was this model working? This model was working. So we have a basis. So we choose basis. So the basis was f1, f2 up to fp. So this basis was such that fi, they are also all functions from Rn to R for every I is equal to 1 to up to p. And then we said we will write down f hat to be equal to alpha 1 f1 plus so on and so forth alpha p fp, right? So that is what we will write down. And how will we find out this alpha 1, alpha 2, alpha p? So the parameters are alpha 1, alpha 2 up to alpha p, right? So these are the parameters that we have. And how do we find out these parameters? So the parameters, the way we find out, we decided was that we will look at this y I minus f hat of xi, correct? This you will minimize. This you will minimize over all alpha 1 up to alpha p. That's what you will do. So this was basically what we were doing. And then I think we defined this in vector form also. Rd was the residual vector, which was basically coming out from yd, which was basically these observations y1 up to y capital N, and y hat d, which were actually the predictions coming out from the model f hat of x1 up to f hat. Okay, so just to make sure that I'm not y1 up to yn and f of x1 up to f of xn. And we showed that this problem can be posed as the least squares problem. It's a linear least squares problem because the model f, the unknowns alpha 1, alpha 2, alpha p, if you look at it as a parameter vector, then this actually for a fixed value of x is a linear function in alpha i's, right? So this is linear in alpha i's. Linear in alpha i's for x in Rn, right? So you fixed x in Rn and then this becomes a linear function in alpha s. That's why this was a linear model. And we actually showed that you can actually work around with this problem, right? Least squares data fitting problem. So the key is to choose the basis. So whatever basis you choose, that type of basis actually decides the model complexity and what type of non-linearities that you want to model and things like that, right? And alpha and alpha 2, alpha p still come as linear, so it becomes a linear least squares problem. So I hope this part is clear, right? So I think yeah, I should not really write this as this, but it should be square and summation I from 1 to capital N. Okay, so basically this is what it is, and in the least squares problem you can write down as RD. So this is same as minimum over alpha 1 up to alpha p norm of RD to norm square, right? So this is what we have, and I think this was the notation that we had used. And in that notation, we had proved that columns will be linearly independent in case when the basis vectors are not redundant or linearly deductible on the given data set. If that happens, then the columns will be linearly independent for the matrix A that we found out. And once we found out that, then we were able to write down the least square solution for this particular problem. So this is the least squares data fitting problem. And similar to data fitting problem, there is another important problem. Which problem we want to look at is the problem of classification, right? So the problem that we want to look at now is least squares classification problem. So let us quickly see what this classification problem is and how can we use least squares to address this classification problem. Okay. So typically in classification problem, what happens is that the data is given as usual x1 up to xn, and the corresponding observations are y1, y2 up to yn. And in the data fitting problem, what we had seen was that these y1, y2, yn actually are any real numbers. Okay, they are any scalars. They can take any real number scalar values, and the functional relationship is from Rn to R. And this R, any real number value could be taken, right? So that's the relationship that is existent between x and y. So f of x is equal to y, right? That's the relationship that we had, and we wanted to find out f. But now, if it so happens that these variables y, these yi's takes values which are only like 2 or 3 or 5, right? So in such a case, this is called as classification problem, or the variable y basically is actually called as categorical variable. This categorical variable actually comes from statistics terminology. Okay, so suppose yi takes only 2 values. Okay, only 2 values. So instead of having it in R, let us say those 2 values are only true or false. Okay, or the value is like yes or no, or the value is 0 and 1. Say, for example, if y only takes these type of values, or -1 and +1, that is what we will consider. So if y takes these types of values, then what really happens? Yi are said to be categorical variable. So this y is actually a categorical variable, and the functional relationship really is from f Rn to -1 and 1. Let us say, for example, okay. So f sends every data point. So every data point either goes to +1 or -1, right? That's the value this data point will take. So it is it is kind of, labels. Okay. So these yi's are actually labels, or in statistical terminology, they are categorical. Okay, so these do not take real values, they're categorical. And the corresponding problem is actually called as binary classification or Boolean classification. Okay. And generalization to this is that, like, only 4 or 5, like finite number of values, 10 values, if these yi can take, then it is like kind of label that will be multi-class classification problem. Here it is a binary or Boolean classification problem. Okay, binary meaning only 2 class. There are only 2 classes. It is either yes or no, right? So it is like pass or fail, as opposed to the grading system, like you have various classes, EX, A, B, C, D, P, and F, right? Otherwise, compared to that, only P and F, right? Pass and fail. So these are the type of classification problems that we have. So this is what we have. And then what is the objective now? The objective now is to find out. So find out f hat. Okay, find out f hat, the model from Rn to -1, 1. And what should this model do? This model should have y hat is equal to f of x hat. Okay, and then this model should as closely resemble with the true function f, true relationship f as possible, right? So that is what we really want to do. What are the typical examples of this classification? I guess there's no need to say, but like fraud detection or email spam detection. Okay, is this email a spam or not? Yes or no type of questions. Okay, or disease detection. Okay, whether you have this disease or not. So these are the type of examples where this type of problems arise. One example that you will the one problem that you will see in your assignment is basically of MNIST data set. Okay, in the MNIST data set, there are 0, 1, 2 up to 9 handwritten digits, right? And those handwritten digits actually you have actually already worked with them, right? You already have done some problem. You have done k-means clustering on these digits already. So what we want to do is that we want to do this least squares clustering also on these MNIST data points. So what we really are interested in is, for example, we want to check given a handwritten digit, given an image, whether it is, say, for example, 1 or not, right? 1 or not. So I am looking at this as 1 and all other 0, 2, 3, 4 up to 9 in other class. So this is my class 1 and this is my class 2, right? So for example, the function f is such that it is going from Rn to R. So here n is equal to 784, which is 28 by 28 image, right? So you have that vector. So this x is a vector. So this is an image. And this image is going to either -1 or 1. And what is the relationship? F of x is equal to -1 if x belongs to this 0, 2 up to 9. That means that this is the image, is equal to 1 if x is equal to 1. Correct? So if the image is the image of 1, then you get value 1, otherwise you get value -1, right? That's the way I have this function f. And now what is the objective? The objective, so this data y that I have, so I have this x1, x2 up to xn, right? So this is the data that I have. So this data is actually 784 cross 1, right? So this n is equal to 784 for me in this particular case. Capital N is the number of images that you have, right? So about 60,000 images roughly, I guess you have, which you can use. And correspondingly, what are the values y1, y2 up to yn? So these are the labels. These are the labels that I have, and these labels will be +1 or -1 based on what is the image that you are really looking at, right? So these are the labels that I have, y1, y2 up to yn. So that's how I have my data. That's what I'm really looking at. And when I look at this particular data, what am I really interested in doing? Obviously, I am interested in learning this mapping f, right? So I am interested in learning in mapping f. So what will I do? I will try to come up with a model f hat, right? So I will try to come up with the model f hat, and this model f hat will be from Rn to R. And what will I try to do when I do this prediction yi hat? This yi hat be as close to yi as possible. Okay, but now the thing is that this as close to yi as possible is little weird, right? Because y only take two values, -1 or 1, and now you want this yi hat to be as close to y hat as possible or not. So that is something that needs to be understood clearly, right? So that is what we really will learn, what we really mean by these things. Okay, so like in the case of regression or data fitting, there was this prediction error, right? So there was this prediction error that we had. So the prediction error was basically residual RD, right? So you looked at this prediction yi hat minus yi, right? So this was equal to your ith residual Ri, right? So this is what we had. This was for I equal to 1 to n. But here, because yi hat will take only value +or -1, and yi will also have value +or -1, these errors can actually be interpreted in a different way, right? The misclassification rates or correct classification rates, right? Whether you classified it correctly or not. So that is something that we can look at through something which is called as confusion matrix. Okay, so there is a concept of confusion matrix. So this confusion matrix actually will help us in understanding how these things are, right? So there are 4 different types in this binary classification, which we can generalize. So first is true positive, then true negative, and then you have false positive and false negative, right? So false positive and false negative. So how are these 4 terms defined, right? So y was actually equal to +1 and y hat was also equal to +1. Okay. So what we have to look at is always y hat, the prediction. Okay. What is this prediction? The prediction is positive. So this prediction is positive. So you have this positive here, and y is equal to 1, that is the correct answer. So that was the truth, right? So true positive, so you get true positive. Similarly, in this case you will have y hat is equal to -1 negative, and what is true? Y is equal to -1, that is true, right? So how will you read false positive? So false positive is what? Positive is y hat, right? So y hat was positive, and in this case false positive. So y was actually -1, but your model predicted y had to be equal to 1. And similarly here false negative, right? So false negative, so prediction was negative, and false y is equal to +1. So the true value was +1, but you predicted -1. So this is the terminology. So this positive negative always refers to your prediction, and true and false always refers to your like reference label, right? So whether reference label matches with the prediction or not, that's what you're looking at. So in this 2 particular case, you don't have any error, right? So this is what you desire. And this is something where you have error in your prediction, right? So this is something that you do not want to happen, right? So in certain applications, even if these 2 things are not desirable, sometimes false positive is something that they really don't want to work with. So for example, in disease prediction, right? In disease prediction, so this prediction is saying that you have disease according to the model, but y is equal to -1 says that you really do not have the disease. Okay, so that is one error, and the other error is y hat is equal to -1. So model is saying you do not have disease, but you actually have the disease, right? So like your COVID test nowadays we do. So that RT-PCR test. So what really we want to make sure? We really want to make sure that even in the errors that you have, this type of error should be avoided as much as possible. Why? Because model is saying you do not have COVID, but you actually had COVID, right? So this is the most dangerous situation. Even amongst the 2 errors that you have, false positive and false negative is something you don't want. False positive is still okay, right? You are erroneously detected as a positive patient. At worst, what will happen? You will have to stay in 14-day quarantine at home, right? You will show no symptoms because like you did not have COVID really, but you had to stay in quarantine. That's the worst that will happen. But if you are negative, if you are positive, but test is saying that you are negative, that means that you are free to roam around everywhere and you are still spreading the disease, right? So that is something that is not acceptable. So even both these situations are not desirable. They are still errors. Sometimes in some applications, one type of error is really more critical than the other type of error. Okay, so unlike in regression where all these errors were just put into one basket, right? RI, they do not match with each other. Here, because you are working with a categorical variable or labels, you can further classify those errors in this particular way, and then you can analyze these errors and you can understand what is really happening. Okay, so what are the requirements of the model? Then you can decide if you want to change the model a bit so that you are still minimizing on this and so on and so forth, right? So all these things true positive, true negative, false positive, false negative very nicely can be written in a matrix, which is actually confusion matrix. Okay, so that how does that confusion matrix look like? So it is outcome versus prediction, right? So it is outcome versus prediction. So prediction is +1, prediction is -1, and here you have actual value to be equal to +1 and actual value outcome to be equal to -1. And then this particular entry we will call as number of true positives. TP is true positives. Then this is number of false negatives, right? Because y hat is negative. Then this is number of false positives because y hat is positive, and then this is number of en, right? And based on these ratios, now you can see what is really happening, right? So the total observations is capital N. So like if you add these four numbers, you will get capital N as your total, right? So this is like positive cases, negative cases, and these are like the predicted positive cases in the column and predicted negative cases in the column, right? So that is what you have. So NP plus N is equal to N, and these additions NTP plus NFP is actually number of positive cases, and NFN plus NTN is actually the number of predicted negative cases that you have, right? So this is something that we have, and based on this, people have different names. So I'll just write down those names, right? So one is error rate. So people call off error rate. So what is error rate? Error rate is number of false positives plus number of false negatives divided by capital N, right? So look at these off diagonal entries. Those off diagonal entries are something that are like errors, right? So this is error and this is error in prediction. So you add those two numbers divided by N, that is the error rate. And then the true positive rate, true negative rate, you can have those, just look at NTP divided by NP. So true positive rate. So true positive rate is basically equal to NTP, true positive divided by true positive plus false positive, right? So that is or rather true positive is, yeah, this NTP divided by NP, the total number of positive cases that you have. Then there is something which is called as specificity. Okay, specificity or true negative rate. So this true negative rate or specificity is sometimes really very important, and that is NTN divided by NN, right? So total number of negatives, NTN, true negative divided by like true positive rate. So true negative is called as specificity, and the last one is precision. So these are different metrics to gauge how good your classification is, right? So number of total positives divided by number of total positives plus number of false positives, right? So that is what you have. That is what you have. So true positive divided by true positive plus false positive, that is the precision. Okay, so this precision is
So true positive rate and precision are same?
No. So true positive rate is actual true number of positive cases. So true positive cases, how many, like your labels, in your labels, how many positive cases were there? That is NP. And precision rate is you are looking at these two numbers, these two.
Okay. Here, NTP plus NFP is not equal to NP.
No.
Okay.
May
Okay.
not be. May not be. That's not necessary, right?
Okay, sir.
So what do we do with this problem, right? So the question is, this is what is really happening in this prediction problem, and you will see one problem. You will see one problem related to this classification. So then, what it really means in this true positive, true negative case is that the image was really true, and you said it true. That is true. Image was not 2 and you correctly predicted that it was not 2. The image was not 2 but you said the image is of 2. And similarly here what will happen? The image is of 2 but you failed to identify that it was of 2, right? So these are the 4 different cases that you will look at. So this is the precision, this is the confusion matrix. Okay, so this particular matrix is called as confusion matrix. This confusion matrix is really very important, and you can generalize this confusion matrix very easily in the case of what you say multi-class problem. So here you had 2 classes, so you had 2 square, right? 2 square possibilities, +1 +1 -1 -1 -1 +1 +1 -1, right? So there is a sequence y and y hat, and each star can be put in with -1 +1 -1 +1, right? So there are like those many k-square, right? Those options that you have. So you can generalize this, and you will have k-square options of interest to us, k-square options of interest to us. So it will be represented by a k by k matrix, right? So that k by k matrix is what you look at when you go to multi-class problem. But right now, let us quickly understand what we will do. So now I hope you understand what is the classification problem, and the objective is to find out this f hat. So that's the classification model that we have. So objective is to find out f hat, and what we are going to do, because we have learned least squares, we will find out this f hat using least squares method. Okay, so that's what we will do. Okay, so what we do, we first carry out the ordinary least squares method. Okay, the ordinary least squares fitting of the outcomes. Okay, so when you do ordinary least squares fitting of the outcomes, we are actually ignoring the fact that the outcome has to be between -1 and +1, right? So it has to be one of the values -1 and +1. That fact is totally ignored at this case, because when you have the least squares fitting, you don't know whether it is -1 or +1, right? It can be any real value. In the least squares problem, the outcome was any real value. And here we want values to be exactly -1 or +1, but we will ignore that fact for the time being. So if that is the case, then what do we do? So you choose the basis. So choose basis functions. So you choose your basis functions as f1, f2 up to fp. Okay, and choose the parameters. So the parameters that we have, you will choose those parameters alpha1, alpha2 up to alpha p. And once you do that, what do you do? Parameters. Okay, so once you fix this basis, the parameters are to be chosen. And how will we choose them? We'll choose them in this formula, right? So you have y1 minus f tilde of x1, okay, whole square. So I'll call f tilde. So let me first define f tilde, and then we will see. So define f tilde to be equal to alpha1 f1 plus alpha2 f2 plus alpha p fp. Okay, so you do just that. Okay, and once you do that, then what we will do is you have this f tilde. So you have the observation yi, and you have the prediction using this model for the ith data point f tilde, right? And what do you want to do? You want to minimize this sum of squares, right? I is equal to 1 to capital N. You want to minimize it with respect to alpha1, alpha2 up to alpha p. Okay, so that is what you want to do. So that is our ordinary least squares data fitting problem, ignoring the fact that the prediction of the model was supposed to be between -1 and 1. Okay, so we ignore that fact. And now what I will do, I will now define f hat. So define f hat of x to be equal to sine of f tilde of x. Okay, so what is this function sine of f tilde doing? So what this function really does is the following. So for any real number a, sine of a is equal to +1 if a is positive, and sine of a is equal to -1 if a is negative. Okay, so based on whether the number is positive or negative, just to make like 0 to be included, let us take a greater than equal to 0. It doesn't matter, you can attach it to minus, like 1 also, it's okay. But this is what we do. So sine of A is equal to plus 1 if A is greater than or equal to 0. And what is A here in our case? So in our case, this is our A, right? So this is the prediction. So you look at the prediction. If the prediction is positive, you assign f hat to be equal to plus 1. If the prediction is negative, you assign f hat to be equal to minus 1. And that is what f hat is. So now that f hat, the prediction is plus 1 or minus 1. So based on that plus 1 minus 1 prediction, now you can actually go back to this particular confusion matrix and see what is really happening, right? So that is what we are doing. So where is least squares coming in? Least squares coming in this particular part, right? So disregarding the fact that y was output which was categorical, what did you do? You actually minimize this, right? So you actually did this as a least squares problem. So you had this as least squares problem, and then you modified your least squares by this particular formula. And with this formula, now you are saying that you are predicting this particular thing. Is that okay? Do you understand what we are doing? So again, we have to choose the basis function. So all the results that we will obtain subsequently will definitely be dependent on what basis functions you choose. So again, how do you choose this basis functions? This is like our experience of working with data. Okay, so that is what we will typically do. Okay, and one of the simplest thing that one of the interesting things that people actually do is that they come up with this particular thing. Okay, so f hat x, people actually do is sine of x transpose beta plus nu. Okay, so they use regression model. Okay, so instead of this particular f tilde that you see, they use the regression model. So they just fit a regression model on y, the response variables plus minus 1, and once they fit the regression model on the response variable y, you have that parameter vector beta to be estimated. You can use the estimate using least squares, and once you have that least squares, then what do? You just choose the sign and which sign. So this is a particular case of that least squares model, right? So this is a particular case of that least squares model f hat, where you have f1, f2, fp to be actually the coordinates of x1, x2, xn, right? So that's what you really do. So that's the simple regression problem we saw in the data fitting. That regression is a particular case of this different basis vectors, right? So that's what people do. So in many applications area, people do not actually go that far of choosing the basis and doing this type of stuff. They just do the simple regression on y, x on y. That's the regression that they do, and after doing that regression, they just check the signs, plus and minus sign. So those plus and minus signs actually determine whether you are going into one particular class. Okay, so that is something that really is important. Okay, so one of the interesting things here to note, is that the value of this particular function f tilde, right? So the value of f tilde, so it might happen that f tilde of some xi that you see is either positive or negative and things like that. Suppose it comes out to be 0.8, let us say f tilde of xi is equal to, so xj, other vector, suppose 0.02. What will f hat do to both these values? So f hat xi will also be assigned as plus 1. F hat of xj will also be assigned as plus 1. But you see the values of f tilde xi, right? The value of f tilde xi is this, and this value is this. So what do you want to say about this f hat? Are you feeling comfortable assigning plus 1 in both the cases? What is your opinion? Like, the sine function will assign both of them to be equal to plus 1, but how about f tilde xi and f tilde xj? They have these values, and now you assign f hat to be like this. What do you do in such a case? Are you comfortable with xj classification?
No, sir, it's very close to zero. So the if small errors can like lead to positive, negative, like a wrong classification also.
Yeah.
So we have more confidence in 0.8 to be plus
You have
1.
more confidence in 0.8 than 0.02. At least that's what you are saying, right?
Yes, sir.
0.02, you are not really very confident. Yeah, so that is the general idea in this. So you may be more confident. So there are ways, there are few things people do to avoid such situations or to tackle these things. But what we will really do is we will make use of this idea only in one case where we will do multi-class classification. Okay, so that is the only place where we'll use this particular idea of whether you are really confident or not about these things. But apart from that we'll not really investigate this problem. But this is some problem I just want you to make aware that will exist, and you will have to really tackle this problem in real life situations. Okay, so how do you tackle such a problem in real life situations? That is something that you can actually investigate. You can read more about these things, and you can see what is happening. But this is where I leave this, because this is where actually for me linear algebra application ends, and you can do something more with this. That's something that is not in the scope of this course. But there will be cases where such situation will arise, and when such situation is arising, how do you handle such cases? Okay, so that is something that you have to like investigate further, right? So this is about least squares classification, binary classification. So I can generalize this concept of binary classification to multi-class classification, right? So least squares multi-class classification. Okay, multi-class classification. So what we will be really looking at is again the data x1, x2 up to xn. So these are the data points. So like in MNIST data case, these are actually 784 long vectors that you are really looking at. And along with that, you have labels now, y1, y2 up to yn, right? So those labels are given, and instead of having those labels as only two values, 1 and 2, sorry, -1 and +1, say for example, what you have is you have k label values, right? So the function f is from Rn to R, and that R is not really R. So I will write down this function f as Rn to 1, 2 up to k, where k is the number of classes, right? Where k is the number of classes. K is the number of classes, right? So this is what we have. So given the feature vectors x1, x2, xn, what we really have to do, we have to learn a model. So now what the model should do, so a multi-class classifier. So a multi-class classifier. Okay, so this multi-class classifier is basically the model that we are interested in doing. That's what we are calling. F hat should be a function from Rn to this set 1 to up to k. There are k classes, 1 to up to k. There are k classes. And what should it do? Given a feature vector x, in Rn, it should give me f hat of x, which is one of these values 1 to up to k. So it should assign a class to this feature vector. It should predict the class to this feature vector, right? So that is what we want. And what will you have? You will have a, to check the accuracy, this will be the confusion matrix, right? So confusion matrix, what will happen to this confusion matrix? So this is the output and this is the prediction, right? So this is the prediction. So output is actually 1, 2 up to k. So these are the two true class numbers, and I'll just say 1 hat, 2 hat. So this is like prediction, right? So these diagonal values, k diagonal values that you see here on the confusion matrix. So these k values on the diagonal will actually indicate that you have done your job correctly. The model f hat has done its job correctly, and it has done correct classification. But now there are more errors. What are the more errors? That k square minus k types of errors. So for example, the true output was supposed to be 1, but then you got output as 2 using your model up to output as k using your model, right? So false positive, false negative concept you have to generalize. So it will be like false 2, false 3 up to false k, right? So the model is predicting 2, but the true was 1, true was 2, and so on and so forth. So there will be lot of things that you have to look at, sub cases that you will have to really look at. So those errors are like k square minus k number of errors, and this is the confusion matrix that you will have. And looking at this confusion matrix, now you can decide what are the type of errors you to control more than the other errors if you really want to do something like that, right? But the accuracy can be measured using this, accuracy can be measured using this, right? So this is what you have. So this is what you will get. And now what I really do in this multi-class classifier, I take the idea of one class classifier and I take this idea further, right? So what I am really going to do is a Boolean classifier or two class classifier, to be generalized to k class classifier. Okay. And then what am I going to do? Okay, what am I really going to do is the following. So I will define f hat of x to be equal to argument maximum k is equal to 1 to up to k f k x. Okay, where what is f tilde kx, where fk tilde x is the least squares regression model, is the least squares regression model for label k against the others. Okay, so do you understand what I'll do? What I'm really doing is that I will build k capital K number of models, right? So I will have f1 tilde, say for example. And what is f1 tilde x doing? So f1 tilde x is actually the model. F1 tilde x is actually the model. This model, okay? So this model is going to be that f1 tilde model, right? So this is my f1 tilde. And what is that f1 tilde doing? It is basically deciding whether x belongs to 1 or it belongs to 2, 3, 4 up to k. That is what it is doing. So that is what this f1 tilde is going to do. Similarly, what is f2 tilde x going to do? It is going to check whether x belongs to 2 or it belongs to 1, 2, 3 up to capital K. 1, then you will not have 2, but this thing, right? So if this set I can write down as like k minus 1, right? And then this will be k minus 2, where what is k? This k is actually 1, 2 up to k, this set. So basically I am checking with f1 tilde whether the data point x is in label 1 or it is not in label 1. It is label 2 or it is not in label 2. So on and so forth. Fk tilde, capital K tilde x will be determining whether you have label k or you have label up to 1 up to k minus 1, right? And then what am I doing? I am taking the maximum of all this. And what is argument maximum doing? I am choosing the number k at which the maximum is achieved, right? So I will assign that to be the label of my this thing, right? So this is what is happening. So just to understand this clearly, suppose there are 3 labels. Okay, so capital K is equal to 3. Suppose there are only 3 labels. So those labels are 1, 2, and 3, right? So that is your K. That is your K. So you have f1, f2, f3 tilde. So suppose f1 tilde value is minus 0.7, f2 tilde value is say 0.2, and f3 tilde value is say 0.8, right? So here you will take here you will take f hat of x to be equal to 3, right? That is your prediction. F hat of x equal to 3, which is nothing but argument maximum of these three values minus 0 0.7, 0 0.2 and 0 0.3 and 0 0.8, and this is the maximum value is 0 0.8 and it corresponds to the index 3, so you will take f hat of x is equal to 3. So what is this thing really telling you? This thing is really telling you, so the f1 tilde, so the f1 tilde model is really telling you that x does not belong to class 1, right? The value is negative, so the f1 tilde is going to give the prediction that it does not belong to label 1, right? It is not in class 1, does not belong to label 1. This is telling you that it may belong to label 2, right? But the value with which it will belong to label 2 is 0.2, and this will say it will belong to label 3, but the value with which it is saying it belongs to label 3 is probably higher. So this concept where you had this less confidence in xj and more confidence in xi prediction because of these values, right? 0.8 and 0.2, 0.2. The same idea I used here to say that I have more faith on model f hat f tilde 3, right? So I have more faith in saying that it belongs to class 3 rather than in class 2. So that's what I have done. So negative values definitely tell that that vector x does not belong to those classes. Negative predictions definitely tell that it happens, and positive predictions actually tell you that x may belong to that class. So you choose the highest, you choose the maximum positive prediction, and it is coming by which model you check? It was coming by 3, so you will assign f hat x is equal to 3. That is what you will do. So if you do this, then you will actually get all the predictions, and the predictions may be correct or wrong. So you will put those entries in this particular confusion matrix, and looking at the confusion matrix, you will decide or determine how good or how bad this multi-class classifier work. Okay, and again the same. So this is what you will do, and again the same thing can be done. So this is something that is very useful. So this is the least squares way. Okay, this is the least squares way of looking at this particular thing. So instead of this f1 tilde f2 tilde, again you can use the regression models, and using those regression models you can decide whether it belongs to these things or not, right? So for example, those handwritten digits like MNIST data. So MNIST data has 10 labels, say for example, right? Obviously there are 10 handwritten digits, 0, 1, 2 up to 9, right? So there are 10 labels that you have, and those 10 labels, now you can have this f hat of x is equal to argument maximum of k is equal to 1, 2 up to 10 of these f k tilde x. And what are these fk tilde x? So fk tilde x basically is whether the label is 0 or not, whether the label is 1 or not, whether the label is 2 or not. And for that, you can choose fk tilde x to be equal to this. So f hat k, sign comes with f hat k. You can choose fk to be equal to x transpose beta k plus, right? The regression model. You can choose the simple linear regression model for fk tilde, right? For each class. And then based on that, you decide what is really happening, right? So this is something that you can do. This is something that you can do in order to get the classification done, right? So this is the least squares classification problem, one class multi-class. So that's what I wanted to say about the classification problem. And so you will see naturally this has a lot of interesting applications in many real life problems. But in the assignment, because you have already worked with the document k-means clustering problem as well as this MNIST k-means clustering problem, we will actually continue with those two problems and running problems, and on those two problems you will actually apply this least squares classification in your next assignment. Okay, so that's what you will have to do. And then there will be some additional things about feature engineering that I'll ask you to do in the assignment, which I have not told here basically, but that is about adding randomly generated features to the point, right? So the model that you will mostly use will be the regression model. So you will use simple regression model. So the basis function will be 1 and those xi's, f of x1, x2, xn will be equal to xi, fi. So that's what your f model will be, f tilde basis will be. So you'll use regression models. So x is of size Rn, right? X is of size Rn, you artificially increase the size of this feature vector to be some Rn star, okay, where n star is bigger than n. And by adding some features, so I'll tell how you will add those features. By adding those features, sometimes you get a help. So this is counterintuitive, may not be, immediately clear why this will happen. But when you do the experiment and you actually write the code, you will realize that indeed the accuracy is probably going to increase by addition of these extra random features. Okay, so this comes under feature engineering. So I don't want to get into details of what you are really doing and how it is possibly helping you to get, but I just want you to do this experiment. Okay, it's a fun experiment, and once you write a code for this least squares data fitting and least squares classification, both the cases, I'll ask you to do some few extra simple like few things just to tell that these are the type of things, just to make you aware that this is what can be done. Okay, so this is what I had to say about classification problems and how you can use least squares to do the classification problem. Similarly, what we want to cover is multi-objective least squares and constraint least squares. Okay, so these two types of least squares problems, multi-objective and constraint least squares, also arise very naturally in many applications. So we just want to get introduced to those two problems, and we already have that least squares technique available now with us. How do we solve that least squares problem? We already know. So we'll see how those techniques can be used in order to address this various type of variations of least squares problem. Okay, so least squares data fitting, least squares classification is done. We want to do multi-objective least squares and constraint least squares. Okay, so these are the two things that we want to do, and once we do that, then in the next week we'll go to that decompositions, continue with the matrix decompositions, and we'll learn two more important decompositions: eigenvalue eigenvector decomposition and singular value decompositions. Okay, so these are the two things that we'll start learning from the next class onwards. Okay, anything you want to say? Anything you want to comment on about today's thing? Okay, in that case, we'll stop here today and we'll continue our discussion in tomorrow's class. Thank you.
Sir.